So, Assalamu alaikum and welcome everyone to Approaching Calculus with GeoGebra and Desmos. Now, before Hasan takes over and begins this very exciting workshop, I'd like to take just a few minutes and introduce the Khwarizmi Science Society to those of you who are not aware of the society and some of our activities as well, that what exactly is it that we do. So, our society was founded in 1995, and since 1995, we've been working to popularize science in Pakistan. This includes various public lectures, workshops, seminars, teacher training programs, outreach activities, astronomy festivals. And what we've been trying to do is that we've been trying to make science an accessible commodity for everyone, irrespective of their age, gender, their ethnicity, everything. So a few of the events that we've done include the Falkiyati Melas, the National Science Movement, which was a countrywide, a nationwide movement, and the Lahore Science Melas that have now become our flagship event. The Falkiyati Melas were basically astronomy festivals that were internationally recognized as well. And the National Science Movement included science outreach activities and melas all across the country. Lahore Science Mela is our flagship event, and we do it every year annually. And the next Lahore Science Mela is planned for 2022. And we are looking for volunteers and exhibitors to join the Mela. The Mela is not an exhibition, it's more like a celebration, a festival. It's where elders, really young kids, everyone just comes and enjoys and celebrates science, that science belongs to everyone. Here are a few links, khwarizmi.org, ksslsm.org, and this is our Shutterfly account. I'd really appreciate if you take some time and go through these links to see more of our work. And you can also choose to support us by maybe becoming a member, maybe volunteering for us, maybe sponsoring or donating any of our activities. In fact, Hasan himself is a very dedicated and a keen volunteer who has been part of our various teacher training programs, as well as these calculus workshops and courses. This is just some formal guidelines and rules for the workshop today. In case if any one of you is not named as per what they've registered with, then please, you can rename yourself. You can do that when you click on participants, and when you click on your name, you can rename yourself. It should not be your device name or anything, so that it becomes easier for us to give certificates and everything. While the instructor, that is Hasan, is teaching, we'll really appreciate if you write your question in the chat box or you raise your hand instead of just speaking right away. You are just advised to avoid any interruption, and you're also advised to keep your microphones muted. If in case there's any issue, then I'm here. You can send me a personal message on the chat, you can email me, you can write in the chat box. I'd be there to resolve it, inshallah. And I guess that's it. Just take full advantage of this opportunity, and we really, really hope that this is a useful opportunity for you. Yeah, so over to Hasan.
Thank you so much, Mohsina, for your introductory part. And yeah, welcome again to this interactive session on approaching calculus with Desmos and GeoGebra, which is actually like a free online tools available for us to explore and engage with calculus. Actually, like the motive behind initiating this kind of a workshop is to, like tap this opportunity of using these free resources to really understand and, internalize the very difficult concepts. So, I mean, we just realized, even while I was myself was a student in high school, I just need to memorize lots of formulas and so on. But then, thanks to Desmos and GeoGebra, actually there are even more applications. Now, actually, our life is much, much more easier, only if you know how and when to use them. With this introduction, let's continue. But can you please let me know if you can share if you can see my screen quite well? Yeah.
Yep, we can.
Can you see? Okay.
Yes,
nice.
yes.
All right, so let's move on then. The agenda for this very workshop is, lots of things we're going to do. But since, it's only one-time workshop and we have limited time, even though we have 120 minutes, but I'm pretty sure it's going to, pass very, very quick. So we have lots of things to cover. But what actually I want to emphasize is that, our main agenda is having fun. It is because, there is a pleasure in learning something new. So if you're not actually having fun, that means there is something wrong actually. So I mean, while we continue, I really urge us to be more interactive, and if you have any question, do raise your hand and or comment or write in the chat box. I would really love to be interrupted so that we can make it more meaningful for us. Okay, so these are the agenda. Let's move on. So I am Hasan, as Mohsina introduced you guys about myself. I've been working in for last 8 years and more. Oh, it's a bit old slide, so it says 5 years, but now actually it's more than 8 years. I've been working teaching physics, math, and so on from Europe, from in Asia, and now currently I'm in Africa. So yeah, let's move on. This is not very important. So actually, there are a couple of things we are going to use throughout our webinar. So I want us to maybe to get used to them so that we don't get confused. They might be very, very simple, but since I think we also have some high school students, so I think it's important for them. So the first thing actually we have is delta. So this curly guy, it's like a S, but it has some this shape. It's called delta. You might be aware of this word delta like this triangular shape, but this one actually is the capital letter, but we're going to use the small one in this case, so don't be confused. Then we also have another concept, 1 over 0. So actually this is like the essence of calculus. 1 over 0, actually it tends to infinity. So whenever you have something over 0, it's like it gives us infinity, and it's not easy for us to work on this to calculate this kind of thing. Then we have slope, and the slope you all know is delta y or delta x, right? And that means rise over run. Sometimes we also write this as rise over run. And change in what? But delta here actually means the change. Okay, these three things, we are going to start with this very basic idea, and we are going to build the more concrete concept in calculus. So I think we are okay with this. Let's move on. So first thing first, before we even actually discuss about calculus, let's spend some time. Let's step back a bit and let's think of math. What is math? And so far we have learned so many things in mathematics. So let's discuss a bit and see what exactly we do in mathematics. So maybe right now I want you to maybe write in the chat box. What have you done so far in mathematics? I mean, there are so many different definitions of mathematics. I really don't want to go to same definition, but I just want to approach it in a more practical way. So we have actually covered math we have covered so many topics. Okay. So if you can quickly tell me the topics you have learned so far in math, can you please list it in the chat box? Chat box. Yeah, it's here. So while actually, okay, let me also discuss here, but I also want you to maybe write down something. For example, in math, we have learned parabola, right? Simultaneous equations, and trigonometry, angles, circles, spheres, and circumference, and so many things, yeah? But let's categorize. So let me actually be a bit more quick here. So far, actually, we have learned so many topics, but to be honest, especially in high school, we have covered only kind of 3 parts of mathematics. So whatever we have learned so far, we can categorize them into these 3 parts. First is algebra. Can you guess the second one? Anyone? The second actually is geometry, exactly, and the third one. So basically, if you think of any mathematical concept, we can actually virtually every single concept we can categorize them under algebra and geometry. But there is actually one more branch of mathematics, which is also like a standalone branch. Can you guess that one? Statistics and probability. Perfect. Thank you, MRK and Rafiq. And of course, the fourth calculus, which is maybe we start in school in Pakistan. Actually, we start in FSC in grade 12 or grade 11. So like every single topics we have covered so far, they can be categorized into these 4 parts. So let's discuss about them very quickly so that we can build a very strong concept about calculus. So we have algebra, then we have geometry, we have probability and statistics, and so on. So let's discuss them. What do we study in this kind of branch or field of mathematics? So maybe let's start with the geometry. And if I want to summarize, or if I want to get a key idea of geometry, so we can say the geometry is the mathematics of what? As you can guess, it's the mathematics of shapes, or even space. So essentially, whatever we study in geometry is space. Essentially, we are studying the shapes, be it circumference and angle. Even the trigonometry can also be part of geometry. Okay, and why do you think the shape is so important that we have a very fundamental branch of mathematics that covers the geometry? So why do you think it is so important? Why shapes are so important that we have to learn a special math? We have to develop a special math on shapes. So as you can see, actually, every single thing in the universe, in the physical universe, everything has structure, right? Everything has its dimension. So if you want to understand the universe, planets, be it planets, black holes, galaxy, and even the building, buildings also have shapes, and everything is a single thing. And also, if you go deep down into atoms, the orbitals and the nucleus, and all these things, they have kind of shape. So to understand the universe, to understand the real working of the universe, we need to understand the math of shapes. Yeah, thank you. And that's why shapes are important. So what about algebra? Actually, algebra is a bit tricky. Let's discuss first probability. I think this is a bit easy. So if you want to find a key idea of probability and statistics, what do you think it is going to be? Estimation. Okay, sorry. So algebra, the probability and statistics actually is a randomness estimation. We have Naresh saying, actually, statistics has to do with the randomness, but I think a better word would be chance. So the probability and stat is a math of chance. And of course, as Naresh is suggesting that it is also about the randomness, so that is also possible. But can you make yourself aware of the reason why the chance or randomness is so important that we have to study them in detail? So anyone, is there anyone who can think of a reason why chance are super important? Okay, so the reason actually, this happens actually, earlier people used to think that the universe is very deterministic and everything is perfect and, all those Newton's laws and so on. But then, sooner we just realized that every single thing is just the probability or the chance. So for example, we humans or everything else are made up of atoms and fundamental particles. So the fundamental particles are themselves are, when we want to study them, we have to study their position and so on. So their position actually, they are simply a probabilistic value, okay? So they don't exist physically. For example, a single electron has no volume, a single fundamental particle. So what they have actually like a mathematical or probabilistic value. So to understand the very fundamental particles, we need to understand the very idea of statistics. And there's so much thing. But since the topic is about calculus, let me simply stop here and let's move on to algebra. Okay, so algebra, here we have, algebra is a bit tricky, but let me just simply give you the word. There are so many words actually we can use to describe, but it is connections or relations. So what actually algebra does, it finds a relationship between different numbers. And how it does so. So for example, let's discuss a very, very basic example of Pythagoras Theorem. So let's say if this is 3 and this is 4, and this is, then we know this is 5. So basically it connects, it gives you a formula or formulation between different numbers, and then it also gives you a toolkit, actually C squared, a toolkit to solve different values of equations. So it makes it takes some numbers and somehow it gives you some kind of equation out of those numbers. So for example, this is one of the famous example. We also have more examples. There are more identities. For example, sine square x plus cos square x, which you are I think are already aware, and so on. We also use algebra to solve equations. There's also a very strong domain of algebra, but essentially it is about finding the relations about different quantity. Okay, so now let's move on to our main idea here, the calculus. So what could be the one word that can define the calculus? So calculus is the mathematics of what? So anyone can anyone think of a word? Yeah, we got some answers from Naresh, from Noor. Actually, the calculus is the math of change. Exactly. And actually, maybe let's ponder for a while here why the change is super important. So we have learned about the shapes and chance and this relationship. Let's discuss about the change. Why do you think the change is important? I mean, if you understand the importance of change, we are also going to understand the importance of calculus. So calculus, why do you think the change is important? Or let me ask you in a bit different way. What are the things that are changing? So actually, if you think change is permanent, we have got some answer from Munawar that the change is permanent. Actually, that's very true. You know, there's only one constant in the universe, and that is change. Change is the only constant. And of course, you know, because everything depends on time. So as the time changes, everything is changing. Everything also changes. So for example, we also grow. The plants also get taller and taller as the time passes. The planets move. Electrons also, are the fundamental particles. They also change their position and their momentum and so on. So actually, every single thing is somehow in a kind of in a race. So everything is changing. That is why the calculus is a very powerful tool humans have invented to understand the very nature of change. Okay, because change used to be like more like a philosophical idea before, but after the invention of the calculus, or you might want to call it discovery, people realize that then we are able to understand them, and once we understand, once we are able to find a mathematical equation of change, then we can also predict the future, because once you have a mathematical formula, depending on time, you can simply change the value of time and then see how the particular thing is going to be in the given time. So that is why actually it is very super important to understand about change. So that is actually going to be our starting point. We are going to start with the very idea of change, and we are going to build up the concept of the whole calculus. We will try our best. Of course, we will not be going to cover every single topic here, but again, the idea here is to use Desmos and GeoGebra, and maybe to get some basic idea of what calculus is. But our starting point is going to be this word, change. So keep that in mind. And actually, right now, I want you to do this activity. It's like a kind of game. Actually, the very idea of why I'm doing so, it is about pre-calculus. So I want to see like how is your level, or about the participants. What do you know about the pre-calculus idea? So I can also discuss those things while I continue. So I want you to maybe open a new tab if you're using your laptop, or you can also use your phones separately. And there's an instruction here. So you should be going to this website, joinmyquiz.com. And if you enter this code 006285, there will be around 23 questions, but they're very very straightforward question, and you should be able to answer them in less than 30 seconds, and so on. Okay, so please do join this joinmyquiz.com, and let's play this game. And once I have the clearer picture of the audience, then we are going to I'm going to tailor-made the rest of the slides accordingly. So please do join. I think you can see my screen. Yep. Once you are done, can you also write in the chat box that I am in? I can also see you, by the way, but I also want you to maybe write it here. Let me see how many participants have joined already. Yeah. Okay, so please do join. And Mohsina, if you want, you can also stop the recording, because I think for next 5-10 minutes, we don't need the recording here. Let me simply let me end here, and let me also discuss a couple of questions. I think I got some questions from on the chat box also. I might be discussing them. Let me just show you here. So Ghulam Farid is saying graph of 1 over sin x. Okay, so I think let's continue. What I see here, I think the question number 9 or 10, it was most confusing. Okay, I will be discussing these topics while we discuss, continue our next slides. Okay. Of course, you can also ask me, because the concept or the questions you have been asked in this quiz, we are going to use it throughout the slides. So please do ask me. I also found out some of the questions, so I will be also addressing them while we discuss the very idea of calculus. Okay, so yes, Ghulam Farid, I got your message, the graph of 1 over sin x. So I will be discussing that thing also very quickly. Let's move on. So where were we? Just here. Okay. Give me a second. Yeah. So we have learned, that the change is the only constant, and the calculus helps us quantify or find get a mathematical formulation of the change. So that is why calculus is super important. And once you do any advanced kind of engineering programs and so on, you are going to see calculus everywhere, starting from, of course, physics, but economics and engineering and so on. So before actually I move on, so if the change is the only constant and the calculus is the math of change, so maybe do you remember anything you have learned so far about change? I mean, it doesn't have to be from calculus, from the idea you have been given in your math course, maybe in the primary or elementary school, because we want to build the concept from the thing which we already are familiar with. So can you remember? Can you tell me what exactly is the change? Not from the calculus point of view, but from the primary mathematics or elementary mathematics. Yeah. Have you ever learned about change or any formula you know about which describes change in something? Yes. Anyone? So yeah, actually we learned about change, and the change, and actually even in grade 5, or I believe it can be less than even in grade 3 or 4. Yeah, but actually Imran is saying it's velocity or acceleration, but that is actually it tells you the change in the distance. For example, velocity tells you the change in displacement. But I'm talking about the general, like the very core formula of change. And I am pretty sure all of you have seen this equation, this acceleration and so on. They are actually like some application of change, but not exactly. Actually, Ghulam Farid is saying subtraction and addition of any number is given number. Okay, the subtraction can give you the change, but it's quite static. It's a bit. It does not actually gives you a full picture. It only tells you like a difference between two numbers, and that's it. Okay, but of course the subtraction, there has to be subtraction kind of thing. But subtraction, because once you subtract, once you minus, then you are actually finding some kind of difference there. So since we don't have much time, let me move on. Actually, the change I'm talking about is the one and only. Okay, Naresh is saying slope. Thank you. Okay, exactly, the slope or the gradient. Okay, and you have been you have seen this in grade 5 or maybe grade 4 and 6 and 7. In every single grades you have been learning about it, gradient or the slope. They are the identical names, slope or gradient. So actually change in y, and someone was suggesting it's going to be the subtraction. So yeah, so it's going to be y2 minus y1 over x2 minus x1. So this is the very idea of change we are already familiar with. Yeah, so the change is this. So this is actually the math of change. So if we want to develop the idea further, we have to start, this should be our starting point. Okay, so the whole calculus actually was, the starting point of the calculus was this equation, which even a child knows. Yeah, of course not a toddler or baby, but a 5th graders or 4th, they know about this idea. So let's move on. We are going to build our intuition of calculus just from the very idea of gradient. So everything else, you might know about those derivative and integration and limits and fundamental theorem of calculus and the volume of revolution and so on. But they all actually start from the very idea of gradient. So we're going to see in the next slides what exactly or how we can develop the concept from here. So actually, before we discuss, let's try to see a big picture, and then we are going to go a bit deeper. We are going to dive deeper, and we're going to see. So we're going to start from slope, and then the slope, actually, we will see there is a problem with the slope. So we will see how we can improve it. So the slope, the derivative is the improved version of the slope. And how do we improve it? To improve, we have to use, it's called infinitesimal or the limit. Of course, don't worry, we're going to discuss them. Infinitesimal, and so to improve the slope, or we have to use limits or the infinitesimal calculus. So then, but just remember the derivative is the improved version of slope, okay? So again, let me repeat. We are now seeing the big picture. Then we are going to dive deeper into each concept. Okay, so then once we have the derivative, then the second thing we have is of course once you learn a concept, then you also are interested in finding the opposite of it. Actually, there is a very, very famous quote in Arabic. It says, "Al-ashya'u ma'rufatun bi-aldadiha." That means actually the things are known by their opposite. So that's actually also very important concept. Once you learn something, or if you want to learn anything, you also want to learn the opposite of that particular things. You have to have a full set. Otherwise, if you don't focus on the opposite, then you might not get the full picture. Okay, so this is a very, very important concept. So once we learn about derivative, we want to find about what about the antiderivative, the opposite of derivative. Okay, sorry, and we will see actually the antiderivative. This comes out to be the integration. Okay, so you might actually think the integration is the opposite of derivative, and that's very obvious. But trust me, the integration being the opposite of derivative is not very obvious. Actually, it takes the fundamental theorem of calculus to ensure that the integration is the opposite of derivative, and we will see, because integration, we know about integration is actually the area under the curve. So how come the area under the curve has to do anything with the derivative or the slope? Actually, let me show you a picture here. Yeah, sorry. I think it's not very clear now. Let me see if I can raise this. Yeah. So you see, this is the integration. Actually, is the area under the curve. Okay, and the derivative is the slope of the curve. And it's actually not very simple, obvious. How the steepness of the curve and the area under the curve, they are not actually obviously related. So many people think they take it for granted that the integration is the opposite of derivative. But it's not very obvious. We will see why is that so. And again, it takes the fundamental theorem of calculus to ensure that the integration is the reverse process of differentiation, which is also part of our workshop today. Okay, so then here, so from the derivative we can also think of the integration here. So this is actually integration, the antiderivative. We're going to see why it is integration, and the limits. Of course, it is we use limits to improve the idea of slope. And once you know about the derivative, then you also find out the maximum and minimum and the optimization and so on. And once you know about integration, then it gives you the volume and the solid of revolution and area under the curve and so on. So again, as you see, the starting point was the slope, okay? And then from slope, we went to derivative. And once we found the derivative, we found the antiderivative. And then it happens that the antiderivative or the reverse derivative was integration, and which was an area under the curve. Then we extended the idea of the area under the curve to find the volume and so many things, yeah? And of course, the idea of derivative also gives us the idea of optimization with minimum and maximum problem. Actually, Naresh is saying integration is all about finding area. Yes, I mean, integration gives you the area under the curve. But my point here actually, once you integrate, we know the integration is the opposite of derivative, right? But why is that so? So we will see actually this very idea. So be with me, and that is going to be the main theme of this workshop. Always gives me area under the curve. Yes, it always gives you, if you integrate from one point to another, it gives you area under the curve. But again, why integration is the opposite of integration. So be with me, Naresh. I will discuss this thing, when we discuss about the fundamental theorem of calculus. So let's start with the idea of slope. And we learned because the slope is the starting point. So let's talk about the slope and so on. But before we do so, let me actually introduce you, discuss a brief history, because that's also, it's very important for us to see the things in connection, how the things are connected, okay? Thank you, Naresh. So the calculus actually, to be honest, when it was discovered or invented, depending on the how you want to perceive it, there were two scientists in the recent time, around 1700, Gottfried Leibniz and the one and only Isaac Newton. So these two people independently, actually they were in the same time era, they were present. So they discovered the calculus, and the reason for them to discover calculus was different. I will actually start with the Newton's idea of calculus, and actually it is called infinitesimal calculus. And later on we just simply dropped the name of infinitesimal. We simply stick with the only calculus. But the full name was, when it was invented, infinitesimal calculus. And there's a reason why they use this word. But first thing first, the literal meaning of calculus is actually a small pebble. Yeah. So because it was used to count in the olden time, people used to count many things with the small pebbles. So the name actually came from there. Even the word calculator and what else? And actually calculus is also used sometime if you have any small pebble in your teeth. The doctors say that you have calculus in your teeth, which is not a good thing, by the way. But yes, the meaning of the calculus is pebble, which is used to calculate things in the olden time. Okay, so as I discussed, it was discovered by Gottfried and Leibniz and Isaac Newton. So, for example, why it was discovered at first place? I mean, again, it is very, very important. Once you understand any concept, it is very important to relate yourself with the idea. So yes, so this picture, and I think everyone knows about this thing. There's a guy sitting there and falling from an apple, and what happened then? Do you know? According to the story, it might not be actually like the real incident, but this is actually like the story, or people used to say this. But do you know what happened next when the Newton saw that the apple is falling on Earth? Many people actually think that he just discovered the gravity, which is actually kind of absurd, because the gravity, everyone knows about the gravity. Even a child knows. That's why that a child does not simply walk on the window and then simply, because he knows if he continues, he might fall down. So what actually Newton discovered that time is that the apple coming to the earth because of gravity, it is the same reason the moon is held on the space. People used to think, well, how come the moon is there? And they used to have a two different theory of gravity. One is for the things which are on the space, the objects in the space, and the other gravity for the thing which is on the earth. It is because, if it is the same gravity, then according to the same idea, the moon should fall on earth. So people were perplexed, and actually the Newton realized from this incident that it is the same gravity, and the same gravity actually also enforce you to think that the moon is falling, and that is true. So moon is falling. He just realized that, yeah, moon is also falling, but because of the curvature of the earth, if the moon is falling on the earth, so it continues falling and falling and falling and so on. So it starts making a circular path, but essentially it is falling. And that is actually very idea on the spaceship or International Space Station. You see that the scientists, they are floating. It is not because there is no gravity of the earth, because they're not actually very far away. I think they are only 400 kilometers or so above the earth, which is not actually very far, and they have very strong enough gravity of earth, but they are still in a free fall motion because of the reason that they are falling freely on earth. But because of the curvature of the earth, they don't hit the surface, but they are in a free fall. Okay, so this was actually the idea, and then the Newton wanted to make a calculation, and he was of course studying the gravity, and he just realized that the gravity is inversely proportional to the distance. As you go away from the object, then the gravity reduces. But the thing is that the curve actually you see here is not a straight line, and he wanted to understand how the gravity is changing through the distance. So he wanted to understand the idea of this, like the change in this curvature. But there's a problem, as you can see here. If you use the same formula of the slope, let's say for these 2 points, point 1 and point 2, and then it gives you the slope or the change. But if you take the points, maybe not here, somewhere else, let's say one point here and the other point here, then the slope changes also. You see, the slope is changing throughout the curve. The change is also changing, and that means in order to use the slope formula, it is not possible anymore because it does not give you the correct definition. So basically, the Newton started with this idea of like he just discovered, and like he spent more time how to understand this thing, and he came up with the idea of the derivative. Okay, so we're going to discuss them in a while, but very quickly let's go through wait a second, some functions because we're going to see them. Here actually, he thought basically he was using like a circle, but let's think of this this curve. So you see here, if you have a curve here, and if you join these 2 points, because in order to find the slope, you need 2 points. And the second is defined as delta y or delta x, which is the slope, this formula. But if you go down the curvature, down and down, you see these 2 points, they become smaller and smaller. So the delta y becomes so small, so tiny that when you reach at the point tangent, so it becomes 0. Okay, so delta y becomes 0, and delta x also becomes 0. And now actually it's an issue because of the reason that if something is 0, if you are dividing by 0, then we cannot actually do any mathematical calculation. But here comes the genius of Newton. Since you also have the top function, the numerator also goes to 0. That means once you simplify these two guys, you might get some value, and we will see them in a while using the Desmos. What does it mean? This is called the limiting value. So here comes the idea of the limit also. So I'm going to discuss them in detail on Desmos. So I'm just giving you a bigger picture. Okay, so where were we? So the idea that if you go very, very tiny bit on x-axis and also on y-axis, this infinitesimal change, as you can see here in this zoomed in picture, then you are able to find some meaningful value. And why is that so? Actually, let's discuss this idea now. Let me share my screen with the Desmos application. So wait a second. You might also know. Let's do it. Sorry. Let's do it with a particular example of the sine x over x. Okay. So we all know, if when x is 0, when x is 0, let's say what happens to this function when x equals 0. So you see here, when x is 0, so if you can also use your calculator, sine 0 would give you the value of 0, and when x is 0, then x is also 0. So we have actually this kind of dilemma, 0 over 0. So what does it mean actually? Once you study calculus, you have been introduced many different theorems, like let's say, for example, sandwich theorem and so on, to prove that this equals 1, or L'Hopital rules also. But let's see from the graphical perspective, or from Desmos, what exactly is sine x over x. So I think you can see the screen. Let me open this application first. Let me call it Desmos. I will also be discussing the idea on GeoGebra, but in a while. So can you see my screen, by the way? Can you see my screen? Yes? Okay, thank you. So just let me click here, graphing calculator. And as you can see, you will end up, this is the interface of a very strong and powerful graphing display calculator. So let me simply type here sine x. And we have a very nice picture of sine x, you can see here. Okay. And let me also sketch a function of x only. So we have these two functions, sine x and x. What happens when we divide these two guys together, sine x over x? So when we divide, actually, let me try to zoom in to this function. If we zoom into this function, as you can see here, when we go very, very close to 0, you see, when we go very close to 0, sine x and cos x, they are essentially the same thing. Okay, not exactly at 0, because at 0 it will be 0 over 0. But let's say, once you are at this point, or at this point, for example, you see the value of sine x and the value of x, they are the same thing. That means they are going to cancel each other. Does it make sense? So as you go very close to 0, we see that the sine x and cos x, they become the same value, they become the same function. So if you have same thing, and if you divide the thing by the same thing, we get the answer as 1. So when we actually, let me write this way, not this way, when you have sine x over x, and when x goes to 0, so let me write here, this is a fancy way of writing, x goes to 0, so limiting value of x when it goes to 0, since sine x and x are the same thing, they cancel each other, and that's why we get 1. Okay. Okay, what happens when we have, let's say, cos x over x? And let's also discover cos x minus 1 over x. Okay, so let's see what happens in these two cases. Let me sketch the graph of cos x now. Okay, and let me actually turn this graph of sine x off. Second. Okay, let me write here cos x. Sorry. So because this function Desmos is case sensitive, I need to write in the small letters. Cos x. What happens? Okay, let me refresh. Okay, let me see. Yeah, now I have the function cos x. Let me also plot the graph of x, and let's see what happens when we go very, very close to 0. Let me zoom in. So when you have cos x and x, what happens when you go very, very close to 0? So you see x becomes 0. The graph of x, the denominator becomes 0 before, but the cos x goes to 1. So actually, when you are dividing these two functions, as you can see here, the denominator in this case, when you have the limit x goes to 0, x becomes 0 first. So you still have something here, you still have something, let's say a box, but then this becomes 0. Okay, that means cos x over x will not give you an answer. Actually, it will take you to infinity. So this actually is not defined, or actually the answer would be like a very, very big value, because this time you are dividing by 0. Okay, so cos x over x will give you infinity or undefined function. What about cos x minus 1 over x? So let me try to sketch here. Cos x minus 1. Okay, let me turn this off. If I click on this red dot here, it is going to turn the function off. So I have, okay, so this is the blue function, x is the blue function. If I zoom into this function, okay, what do you see here? Cos x minus 1, which is the green function, this becomes 0 before x becomes 0. So for example, at this point, the cos x minus 1 is already 0, but then it has some value. So let me go back to the slide. That means if I have this limiting value, limit x goes to 0. So we have 0, and then x is still something, right? I don't know the value, but it is still some positive value. So that will give you 0. Okay, so this is the idea actually why this limit works. I mean, you have been used many different methods, but on the background, when you see or not. Okay, so are we together? Okay, thank you. Okay, let me move on. Actually, there are actually so much things to discuss about limit, but since we have only limited time, let me move on and to the idea of derivative. We are also going to do an activity on the GeoGebra and so on. But before we discuss about the derivative, we need to understand a couple of things because otherwise it won't make much sense. The functions are super important because we want to find change, and since it is about math, so we want to change in functions. So we have a different type of function, but we can also categorize them: polynomial functions, trigonometric functions, and logarithmic and exponential. And we also have some other functions, rational functions or root function. Let me move on. Polynomial functions are very nice, well-behaved function, and they are actually different types of polynomials. The first thing is constant and linear and quadratic and cubic and quartic. So these are all polynomial functions. They are super important is because they are very, very well behaved function. So if you want to maybe make a mathematical model of a physical phenomena, you actually want to model them in a polynomials because they are very well behaved. There is no sharp turns, there is no break. So they are actually very nice and well behaved function. Let me move on because of the time restriction. Let's move on. Let's move on to the second type of functions, which is trigonometric functions. And you know about trigonometric functions, sine, cosine, and tangent. And you know about, for example, if you have a triangle like this, theta. So sine theta is defined as opposite over hypotenuse, right? Opposite over hypotenuse. But there is actually a very, very severe or subtle problem with this concept. If you define sine theta as opposite over hypotenuse, then we are in trouble. Do you see the trouble? Sine is p over h, hypotenuse, but that is actually, if you define the function, sine function this way, then it is going to, it will provide you a very huge trouble. And actually the problem here with this concept is that the theta cannot be more than 90. You see the problem? Because if you define this function with respect to triangle, then it is only defined for the theta less than 90 degree, because this theta cannot be more than 90 degree. Okay, so this is the definition of the sine theta based on right angle triangle is not accurate, or is not perfect, or it has a problem. We have to update the concept of sine theta and cos theta, and for this actually we use the idea of unit circle. Again, it is also a very huge topic, but let me just give you a glimpse of the concept. So how do we define sine theta or cos theta or sine alpha? is, if you have a point which is moving on the, actually, let me show you here. If you have a unit circle, so basically the x component, you can of course just you can divide this point, this hypotenuse into two components. So this component is given to you as cos theta, and this component is sin theta by definition. And as you can see here, as the point move on, then you can see that the theta can be more than 90. It can also be negative if you go in the anti-clockwise direction, and so on. And I'm sorry, actually, I have more things to say about this, but because of time restriction, let me continue. But please be aware that the trigonometric functions, they are better defined on the unit circle, because the very definition of triangles are not exact or accurate, or it has loophole in it, because the theta otherwise will not be able to reach the value of 90 degree. Okay, but if you define them through the unit circle, it is much easier. Okay, so here we have the function of sine function, and this is the cos function. You can see why is that so. Let me move on. Let me not discuss this right now, but I want you to maybe emphasize, understand these two functions, that they are the function of sine and cosine. There are more. Let me move on from here. Okay, so with this concept of functions, let's discuss about derivative. We know it's an improved version of slope. Okay, so how do we define? We have the slope as improve this, and we have seen before, to improve this thing, we can simply say that delta y, or delta x, and if delta x becomes very small, this is actually like the improvement factor. This is how we improved the concept of slope, to make sure that you get the change in a curve also. This is given as derivative. So we can say, we call it dy over dx. So this is actually essentially the limiting value of the slope. And as you can see here in this slide we discussed. Okay, there is actually like more definition which is about the first principle and so on, but let's discuss more about, try to understand them graphically further. Okay, let's try to sketch the derivative, because you have been told about, you have seen the formula in your textbooks. Let's not do the same ritual again here. Let's try to see how we can sketch the derivative function if we are given a graph. Okay. So when we there are three things you have to understand. The first thing is that when the curve is increasing, the gradient is positive. So this is important. If the curve is increasing, as you can see here, the graph is going to be higher. Is this? Yeah. The gradient would be positive, and when the curve is decreasing, the gradient is negative, and when the tangent is horizontal, the gradient is 0, and so on. So we're going to use this definition to make the sketch of the curve. So let's start with this curve up here. So as you can see here, at this point, this is the minimum or the maximum. This is the maximum point. So if I make the tangent line here, you see, I can see here that the tangent line, the slope of the tangent line is 0. So can you see? That means the derivative of this function would be at this point, okay? And again, at this point, this is the minimum point, and the slope or the gradient at this point would be this, and the slope of this line, tangent line, would be 0. That means the derivative would be at this point. So what happens before this point? So before this point, you see the curve actually is increasing. You see the curve is increasing. That means the gradient must be positive, or the derivative must be positive. So it will be something like this. You see, it is positive. What happens at this point and between these 2 points? Since the curve is decreasing, it is going down. That means the graph must be negative. But you see, at this point, the derivative is again 0. So it has to be negative until you reach this point. And after this point, you see, the curve is increasing. That means the gradient is increasing, or the gradient of the tangent line is increasing, that means the derivative is positive. So this is the curve, this red curve is the derivative graph of the function, which is given in the blue curve. It is clear, let me discuss these things on GeoGebra, because that is our also main thing. Let me change my screen, and this time I am going to go to GeoGebra now. Okay, so if you basically write here GeoGebra, you will end up on this kind of home page. Let's click on this blue button, Start Calculator. So we are here, and if you know how to type using your laptop, you can also disable this thing. Let me close this. Yeah. So this is GeoGebra interface, and I think the best way to learn GeoGebra is to start using it right away. Let me just discuss the idea of derivative. So to find the derivative of a function, let's start with some function. So let's say I have a sine x, x here. So this is a function f of x equals sine x. Let me change the interface. Let me remove the grid from here. I want the axis. Yeah. So this is actually, it's a very powerful function and app, GeoGebra. So once you type sine x, you see the graph here. And let me actually enlarge the y-axis, zoom in. So if you press shift and if you simply drag your mouse, you are able to change the zoom in or zoom out of the axis. I think this is better. So actually I want to find a slope on this function at some particular point, okay? So I need a point. So to insert a point, you see on the left side, we have these tools, algebra tools and tables. So if you simply click on the tools and you see there are basic tools and other options, I just need a point. So I will click on this point and it says select position or line, function or curve. So I need the point on some particular function. So you see, if I move closer to this function, the cursor changes, and if I click on it like this, now I have a point here. And I can also move this point like this. And if it is not moving, you have to select this arrow or move tool. So you see, I have this point which is moving across this curve. Okay. What I want, actually, I want a tangent line at this point, because we have learned that the derivative is essentially the slope of the tangent line, right? We went from secant to tangent. So I need a tangent line on this point. So again, I will be going to the tools and I need to select construct, because I want to construct a tangent line. So they have actually categorized them into different things. So basically construct, you will go to construct, and we select this tangent. So select point or line, then circle, conic or function. So I will select the point first, then I will select the function. I mean, this will tell the GeoGebra that I want the tangent line at this point on this function. So you see now, we have a point on this function and this is tangent. Yeah. So I need to actually select move tool to be able to move this. So you see now, I can see the tangent is changing. The slope of the tangent is changing. And if I am at the top, the slope of the tangent is 0 because the tangent line is simply horizontal and so on. 49 to x plus 0.35. And if I go to the top value, peak value, you see the slope would become 0. Okay, so let's define m as a slope of a function. So if you simply write slope, and because g is the tangent line, let me write here g here inside. So the GeoGebra can find the slope from here. As you can see here, it is negative 0.007, and that's why you have the same slope here. Okay, if I move it, and this also makes a nice triangle with the horizontal width of 1. So you can simply compare the value of slope. So 0.75 now, and as you go along, at this point you see the slope is 1, and that is the maximum slope of a sine function is, by the way. And as you continue going down, the slope is decreasing, and at this point it is 0 again, and so on. Okay, I think let's be more rigorous in understanding the derivative. Let's define another point, and let's call it d, because I want this point to be representing the derivative. And this function, this point actually d, I want the x value to be the same value, but the y value I want the derivative function, or the y value should be the slope of the tangent function. So the x value is going to be the same as the x value of x. So x of a, sorry, point A, you see that the point A was here. So if I write here x of a, that means the x component of point A. But the y value is the slope, which is m. So let me write m here. So now I have this function d. This will tell you the derivative function at that particular point. If I change it, if I move it up and down, you see this point d is changing. Let me see if I can change the color of this function. I'm sorry. Let me make it red. Yeah. So you see, if I move the point, the derivative point is also changing, the derivative function. To make it more visible, let me also show the trace, and you can also explore. You see how it is changing. So you know, from 0, if you continue, you see the function is positive, and then that means the derivative must be positive. At this point, this becomes 0 because the change is now very, very small. And then if you continue further, you see the tangent line is negative, the slope is negative. That's why you have the derivative function is on the negative below x-axis. And if you continue, it will give you a nice curve also on the other side. Yeah. And if you look carefully, what is this red function? I mean, if you know about this function, actually it is a cos function. So if I even type here, let me see. So if I simply remove this thing, so they actually very nicely overlap. That also means the derivative of sine x is cos x, and we can readily see from this nice looking GeoGebra animation. Okay. Of course, we can explore further using GeoGebra, but let's go back to our slides, and I will come back to this idea on this GeoGebra in a while. Okay. All right, we have okay, we got only 1 hour left. So let's try to sketch the derivative manually, but maybe this time I will not sketch all of them, maybe 1 or 2 of them. So for example, you can see the screen, and let's discuss the derivative function of this quadratic. And as you can see here, the function is going down from here, it is decreasing. That means it is negative in this interval, and after this interval it is positive. So you can guess now it is going to be the derivative function would be something like this. Yeah. And let me sketch for this function, for this quadratic, or with a degree 4. So, yep. So basically, this is the minimum point. That means the derivative function must be 0. So it has to be here and here and here. So the derivative function would be, they have to pass through these three points. And also before this point, the function is decreasing. You see, it is going down. That means it will be negative. And between this point and this maximum point, the function is increasing. It has to be positive in this interval. So let me see, it is decreasing, so it has to be negative. It's here. It is increasing, so it has to be positive. And between these 2 points, this and this, the function is decreasing, so the derivative must be negative. And after this point, it is increasing again, so it's like this. By the way, it is simply a sketch. It's not the exact value. So I'm just trying to show you how the derivative functions works. So the y value might not be accurate, but our target is to understand what derivative gives us. So as you can see here, this is the quadratic function, this function, that means x to the power 4, and the derivative actually happens to be a cubic function. So you can see here, the x to the power 4, if you take the derivative of this function, and the symbol for derivative is d over dx, it actually gives you 4x to the power 3. I will discuss why there is 4 here, but as you can see here, the derivative of x to the power 4 gives you a cubic function. And as you can see here, also from the graph. Okay, let me skip this slide. Let's discuss the derivative of sine function, which we have seen already. So as you can see here, from this point to this point, the function is increasing. The derivative has to be positive, but at this point, the derivative must be 0. So it will be something like this. And from this point to this point, the derivative is decreasing throughout. So it must be 0 throughout, like this. Okay, I'm sorry for my drawing. And then from hereafter, it will be increasing again. So as you can see here, the derivative of sine x is cos x. There are also other methods to prove from the first principle and so on, but I think it's better to prove at least once visually. And the cos x, as you can see here very quickly, the function is decreasing throughout from this point to this point. That means the derivative must be 0. So, sorry, the derivative must be negative. So yeah, it's like this. And from this point to this point, it is increasing. The derivative must be positive. And as you can see here, this function is kind of sine x, but not really. The derivative of cos x is actually a negative sine x, because as you can see here, the sine x, it is a sine x, but it is only flipped on x-axis. So it is negative sine x. Okay, then we also have the derivative of exponential and logarithmic function. They are actually very interesting. You don't see here. Yeah. So as you can see here, let's discuss about this exponential function. What is happening to this function? It is increasing or decreasing. So as you can see here, it is increasing, but it is always increasing. Okay, that means it is never be 0. It is always increasing. Okay, so the derivative must also be always positive. Make sense? So can you make a function which is always positive? If you make this, for example, if you come up with this idea, okay, this is a function which is always positive, like this, like a line. That's not true, because if you extend this line, if you extend this line, it becomes negative. So this straight line is not the solution, it's not possible. So think of a function which is always positive, and actually it happens that the function is itself. So the derivative of exponential function is the same, like it's going to be the exponential function again, because that is the only way. If you extend either way, if you extend this function on the x-axis, on the negative x-axis, and extend this function on y-axis, it will always be positive. So this is the only function which gives you not the only, one of the only function which gives you positive value. Does not matter which way you go left side or you go right side, it will always be positive. Okay, then what about that means if you have basically, this is a function of e to the power x, but if you have exponential function, the derivative of exponential function is itself. Okay. By the way, this is the only function in the universe which is also self-derivative. Okay, then we also have this logarithmic function. Where is that? And the logarithmic function, as you can see here, it is increasing. This is also positive. You see, it is always increasing. That means the derivative must also be positive. But the thing is here is that, in the beginning, the rate of change or the rate of increment or the rate of the slope is also increasing. That means in this interval, in the beginning, the change was very, very sharp. There was a very sharp change. So that means the derivative function must be very, very big at this initial point. And it happens that the derivative function would be something like, in the beginning, it will be at the higher value. And as you go away from on the x-axis, the derivative function would also be decreasing, but it will never be negative. Okay, so it happens that the derivative of ln x, let's say if it is ln x, and if you take the derivative of this function, this gives you this curve. Can you guess what is this curve, by the way? This curve is rational function, which is 1 over x. All right, so this was the derivative of these functions, and I'm sorry I just went very quick because of the time limitation. So there is actually a list of the formula which you have been given, but I really urge you to maybe sketch the graph of the function on GeoGebra also and see how the function is changing, and then you should be able to find the derivative functions by the graph, and it will be more inspiring and motivating. Okay, we also have some rules for derivative, power rule and basic functions and chain rules and so on. And I don't think I would be going through all these rules, even though there's also like a very interesting and intuitive explanation. But maybe we need to skip these things because we also need to cover something on integration. But before we do so, since we have learned about derivative, I want you to go back to the GeoGebra again. But this time I want you to try something, and yeah, here you are. So please go to this website, www.geogebra.org/groups, and then enter this code, WSSBT. So can you please do so very quickly? And then you will see there's an assignment for you, a very quick one. So let's spend maybe next 5 or 7 minutes on this. So all of you, please go to this website, geogebra.org and /groups, and please enter this code here. Let me also share my screen here. Is that? It is here. Okay, so once you are in, let me also show you from here. Yeah, I think you can also see this screen. So you can go to this website, geogebra.org/groups. Okay, let me also type this on the chat box, then I think it will be easy for you. Sorry. Where is the chat box? So once you click on this, then you should be able to write down this code. Let me also give this to you. Here. Okay, let me see how many of you have joined already. So we have got one participant. Let's wait for some more people. So please do join this, and you know how to do so. You have to enter WSSBT on geogebra.org/groups. Okay, then you should be able to see this activity. And I want you to try, you know, you have to move this white dots up and down. And then you have to move in a way that, you know, this white dot represent the curve at this point on the curve. So if once you move it down, it gives you a slope, the value of the slope of the tangent line at this point. So you have to adjust these points so that you get a nice tangent on the curve throughout. Okay, and then, you know, let me not do it for you. I want you to try yourself. So, and then see what kind of shape you get from here. So make sure that you only change the white circles, not the red ones and the green ones, because it might change the shape. But if you have done so, you can also click on this arrow, this undo button, so it can also undo it for you. Yeah, and then you also have to give these answers. So let me see how many of you are here. So Nimra and Timur and maybe Mohsina, are you able to access this activity? Can you please let me know? Thank you. So can you please work on this activity? It's a very small one, you know. Actually, earlier in our longer courses, we did more advanced activity, but let's do it very like an easy one. But this is also very revealing. You will see what exactly the derivative is with respect to the curve itself. So please work on this, and let me also see your activity. Okay, I think Imran Bilal, I think is able to continue, but rest are still waiting. So can you please work on this? I can see it here live, how you are doing. And by the way, if you happen to be a teacher, then you can also use this tool to teach calculus, and it's very, very helpful. You can even create all like whole course and quizzes and so many things. Actually, the GeoGebra is also updating its service from GeoGebra groups to GeoGebra classroom, and that classroom is more. I think they have more functions, so it's a good thing. Okay, what time it is now? So it's 2:25. Let's spend maybe 5 more minutes because I see only 4 persons. Are you not able to join other members? Or what? 1, 2, 3, 4, 5, 6. Okay, I see only 6 people here. But let's still spend maybe 5 minutes more. And let's see. Okay, please repeat the task. Okay, the task actually, you know, if you go to this group, then you will end up on this kind of. So, a second. Applet. So, right here. Okay, so your task actually, you can also read this instruction, but I want you to, you know, move these white dots. As you can see here, if you move these white dots up and down, it gives you the slope, the value of the slope of the tangent line at that particular point. So you see, if you go down, so the slope, as you can see here, the slope is negative, right? So the amount, you know, this white dot gives you the gradient of the tangent line at that particular point. So I want you to move this point so that you have, you know, right now this is not the tangent line. So I want you to change this point such that you get a tangent line at this point. Okay, like this, and like this, and like this, and maybe like this, and also like this. Yeah, I think it looks nice. Yeah, thank you. I can see, and then you can also check your answer. If you click here, then basically this is the graph of, this is the derivative function. So you might have realized that what actually the derivative tells you, it gives you the value of the gradient of the tangent line at that point, at every single point. Okay. So can you also answer these two questions? What is the name of the derivative function? So yeah, it's a parabola, as you can see. And the slope at the maximum point here, or the minimum point, is 0, as you can see here. So let me see. Imran has done the task. Okay. Okay, we have maybe 2 more minutes. So maybe the rest of the people, you can continue on it. See. Okay. I guess you get the idea. Of course, you know, I will keep this group open, so you can also work on it later on. I think it's time for us to move back. Okay, Naresh, if it is not working, okay, thank you. You can do it later. I will still keep the group open. I might also, if you want so, I can also add some more activities. So you can also play with that. Okay, thank you, Mr. Ghulam Farid Tumrani. And let's move on to our topic. All right, we got only 30 minutes, or actually 40 minutes, but we have, what do we have left? Is that? Yes. Okay, let's get back to our idea of the derivative. I told you there are so many rules of derivative. I will not tell you, right now, because you can find them also in the book. So you will see them, the power rule, and also the product rule, which you know about the product of two functions, and that is given this way. But we can also understand them through graphically, let me not do it now. Yeah, let me skip this. But there's also like an intuitive way to understand. If you are interested, you can of course approach me. Maybe once we finish the workshop, maybe I will tell you what does it mean. Let's move on now. The chain rule, the quotient rule, is it here? And then we also have the chain rule. Actually, the chain rule, I want to maybe spend a couple of minutes because that is actually a very interesting rule. And many people sometimes they don't take it as they should take it. So the chain rule actually says that, for example, if we have x to the power 7, and if you want to find the derivative of this x to the power 7, we know this is going to be 7 times x to the power 6. But actually that is not the case, to be honest. We still have to continue. I still need to multiply this with the derivative of the inside function. So you see, like inside function, we have this x. We have some function x, and that function has power 7. So the inside function is x. And if you tell me the derivative of x is, the derivative of x is 1. So I need to actually multiply with by 1. But we don't do so is because, if you multiply by 1, it is still be the same thing, okay? But the idea is very important. Once you differentiate or once you find the derivative using the power rule, you use the power rule and then you have to multiply the answer with the derivative of the inside function. What actually it means? It means this. So for example, if you want to find out the derivative of sine x to the power 7, okay? So what happens in this case? We know the derivative of x to the power 7 is 7x to the power 6. And what actually the x is, x is a variable, right? So by definition, a variable is a thing which can be anything, right? So x can be anything. X can also be sine x. So you see, in this case, x can also be sine x. So I will just pretend that sine x, like here actually we still have x, because x can take any shape or any value. So that means if x can be sine x, I can simply use the power rule here, and that tells me the answer is going to be 7 times x to the power 6, and here x is sine x. So this is going to be 7 times sine x to the power 6. But as I told you, we should not stop here. We have to continue. We have to multiply with the derivative of the inside function, right? So what's the inside function? The inside function is sine x. And what's the derivative of sine x? So we have seen this also in the previous slide. The derivative of sine x is cos x. Okay, so that is actually the chain rule. So if you understand it like from the code, you will be able to solve maybe very, very complicated question and so on. So for example, let me find some nice question for you. Yeah, you see here, for example, let's try to find the derivative of this function. And let's even let me write it down here, sine, and then we have 5x cubed plus 2x. And let me even make it more complicated by putting 3 here. Okay, and if I want to find the derivative of this function, I will simply use the chain rule. And I see here, first of all, I will start with the outermost function. And the outermost function is something to the power x, right? And this something actually, it is x, because x can be anything. So x can also be sine of 5x cubed 2x. So I will pretend that this function inside this is x only. So I will start with the outermost function, and that tells me actually this is going to be 3 times sine and 5x cubed plus 2x, and because this is x, and to the power 2. Okay, but then I will not stop here. I still need to continue. I need to multiply with the derivative of the inside function. So I will go one step inside, and I see here inside we have sine function. So I will multiply this with times the derivative of sine function. And if you remember, the derivative of sine function is cos function. So that is going to be cos of 5x cubed plus 2x. Okay. So, but then I will not stop here. I still have to continue until I reach the very, very core function. I will still go one step further more, and I see here, now we have 5x cubed plus 2x. You see? So I need to multiply with the derivative of this function. So let me write it here. The derivative of 5x cubed is going to be 15x squared. And plus the derivative of 2x would be 2. That's it. So you see, like you might be told that you have to use the substitution method and so on. But if you really understand the very idea of chain rule, you can solve many like complicated functions and so on. If you simply follow the procedure that you have to multiply with the derivative of the inside function. And also the power rule is really a power rule, because you know you can change x with any function. Okay, so and by the way, if for some of you, if you find it very advanced, you know, this topic, but because you know, since we have a like mix of participant, that's why you know I'm also introducing you with this idea. All right, so let's move on with the derivative, and also you know we can use the optimization, because the derivative at the top point or at the minimum point it gives you 0. So we can use this very idea of a maximum and minimum and the fact that the derivative is 0 to find or to optimize many different functions. But I'm not going to do it right now because I want to do now the next big part, which is antiderivative. Okay, so the calculus, which is the math of change, and that answers apparently like seemingly impossible question. So we have actually 2 impossible questions, seemingly impossible question. The first one is, how can we find the instantaneous change? And why this is kind of impossible question? Because once you want to find the change, yeah, right? We want to find, I mean, if we find change from the slope, and to find the slope, we need 2 points. So for example, if you want to find out the speed, you need 2 points, but right? But if the word instantaneous, that means you need to find a change at a particular instant. In other words, you want to find a change at a one single point. And that is actually impossible for us to answer if you don't use the idea of the derivative. So the first part actually has been answered with the help of derivative. And the second part, when can rectangles measure area under a curve? Okay, so this is actually like the second part, and let's discuss this in a bit more detail. So the first thing first, as I told you, that the things are known by their opposite. Okay, and that is actually a very famous quote in Arabic, and which is also applicable not in math but also everywhere else. If you want to understand anything, you have to understand the opposite of that thing. And so let's try to see what is the reverse differentiation, or sometimes they are also called anti-differentiation. Okay, anti-differentiation. Maybe some of you might be tempting to call this as integration, but right now we don't know what is integration, right? We need to find out what is integration in a while. Okay, so reverse differentiation or anti-differentiation is, I mean, this idea is forward, because if you know how to find the derivative of x cubed, and you know it is 3x squared using the power rule, we can simply find out the reverse. For example, if I tell you that we have a function, and this function is, let's say, x to the power 6, what is And what is the original function? If some function gives you the derivative as x to the power 6, what should be the inverse original function? So of course, if you think carefully, you can also find out the answer is going to be x to the power 7 over 7. So it's more like a thinking process. It's not like there's no formula. You will think of a function when you differentiate that function using the power rule would give you the function. So for example, if I have, let's say, sine x here, so sine x, put it right here. If I have sine x, which function would give you, once you differentiate, would give you sine x? So you can think of like a cos x would give me sine x. Actually, cos x would give me negative sine x. So if I write here cos x, and if if you differentiate cos x, of course you can also use the formula booklet. The derivative of cos x is negative sine x. So to make it positive, you have to also introduce a negative sign here. So the process of reverse differentiation or anti-differentiation is very simple and straightforward. Okay. So we all know how to find the inverse derivative using the formula. Okay, so also there is a formula for the reverse differentiation. If you have x to the power n, so to find the inverse, the antiderivative of this you can get from using this formula, x to the power n plus 1 over n plus 1. And actually I'm not emphasizing here and explaining this because I think you already know about this formula. So let's move on. So right now we are okay with the idea of reverse differentiation or anti-differentiation. Okay, let's move on to the integration then. What is integration? So can someone tell me? The integration actually, actually the integration, the word integration means, as you can guess, once you integrate, you are actually summing them up. Plus a constant actually. Thanks, Ghulam Farid. I did not discuss that thing. Constant thing is because of the time constraint. But yes, integration is the act of bringing together smaller component into a single system that functions as one. Okay, that's very interesting and very like a good definition. But let's try not being very mechanical. Let's try to see what exactly integration is. And since we have seen that, actually, someone of you were asking, is the integration always the area under a curve? Yes, in a normal condition, if you have a curve, let's say if you have any curve, the integration would give you the area under the curve. Okay, but how we can find the area under the curve? Let's say if I have, the idea here is that if I simply take 2 points, point 1 and point 2 here, to find this curve, to find this area, I can split this into small rectangles, small strips, and then I can simply find the area of each rectangles. So you already know these things. So what is the area of a single, if you want to find the area of a single rectangle here, so the area would be, the y value of this function. So the y value is actually the f of x, yeah? And the x value is going to be the width of this rectangle. And let's call this width as delta x. So delta x being the small width, okay? So that means the area of a single strip is going to be f of x times delta x. To find the area of the whole shaded region, I need to add all the small rectangles. Okay, so this area would be the full area, complete area, let's call it A. This will be sigma, so this notation is going to be f of x, let's call it I, and delta x, where I goes from 1 to, let's say it depends. If you want to, if you split the whole area into, let's say 100 different 100 strips, so then this will become 100 here. So the area actually is from 1 to 100, for example. Okay, but this actually, we can find the area this way, but there is actually a problem. If we simply try to find the area of each strips, that will not give me the exact area, because there will still be, if you zoom into this this region, you will still see there is a small gap here. In order to make the error smaller and smaller, what do you think we should do? We need to introduce an idea that we should put infinitely many strips inside. And when we say infinitely many strips, that actually means I will be actually using the word limit. Same function here, f of x I and delta x. But this time actually, if you have infinitely many strips, can you guess what would happen to the value of delta x, this delta x? So if you have infinitely many strips or rectangles, this delta x would become extremely, extremely small. And to write it down, extremely small, I will simply say delta x goes to 0. Okay? And this will give me area. But this looks very cumbersome, and let's replace the whole notation of this limit delta x goes to 0 of sigma f of x I delta x into this form. So let's make it more simple and neat. Let's call this guy. Right now we know this is an integral sign, but in the beginning when it was introduced, actually it was s, like the big S, but now actually the s became the integral sign, and this x and this actually gives us f of x. And we also know when delta x becomes very small, we have a special symbol for that. When delta x becomes extremely, extremely, extremely small, we call it dx. The same thing as delta x. The only difference between dx and delta x is that dx is infinitesimally small. Right now, actually, we don't know what is this, by the way. Okay, this guy, we don't know what is this. This is actually simply we have used that this whole symbol. We can represent this with this symbol. Okay, we have no idea what is this. So let's see what is this. Okay, to see this, let me change the color of my pen. If I can do so. Yes. To do so, let me actually take out one rectangle from here, like from this shape. Let me actually zoom in, and let me just write it like this in a very, very big version. So this is like one strip out of this whole rectangles, and this is like a zoomed version. Okay, so let's call this, this width was delta x. Okay, and this y value is f of x. Let's call it x, and this y value would be then f of x plus delta x, because at this point the value of x is x. So if it is delta x, so it should be f of x plus delta x. Okay. Okay, so now actually let's try to find out the area of this small, tiny strip. Let's call this area as delta A. Okay, so this area is delta A, and we know that this delta A is going to be equal to or more than or equal to, if you think the rectangle, like from this perspective, that this is f of x, and if you think of this rectangle only from, let's say, from here to here, from here to here to here to here. See this small rectangle? If you ignore the top part, if you ignore this part, then actually this delta A would be more than f of x times delta x. And this is the length of the rectangle. This is the width of the rectangle. So do you see it? This is actually f of x. Actually, when you multiply f of x with delta x, it would give you the area of this rectangle. This one, and this one, without the top part. Okay, and as you can see here, this delta A is going to be more than this rectangle. Okay, or maybe equal to if you make the delta x very small. Okay, but this will be also less than if you now look of this rectangle, like from this point. Okay, starting from this point, you go here, the top part. Then if you make this triangle, this rectangle, you see, let me show it again, this rectangle, the big one. How do you find the area of this? So the area of this is going to be f of x plus delta x times the delta x. Okay, so this will be f of x plus delta x times delta x. Okay, so this delta A would be less than this one. Even though I put the equal sign, but actually it can be equal, of course, if the delta x is very, very small. But does it make sense to you? This is a very important step. So the area under this curve is going to be more than the area of this rectangle, this one, and less than this rectangle, this one. Okay, perfect. Now let's divide this inequality by delta x. So let's divide the whole inequality by delta x. So I have it here, f of x is less than equals to delta a over delta x, which is less than equals to f of x plus delta x. Make sense? I simply divided both sides by delta x, and I can do so because delta x is a positive value, right? It's not zero, by the way. It's positive value. So I can basically simply divide both sides, or divide the inequality by delta x. So what happens now? Actually, you see here we have delta a over delta x, and this function is more than f of x and less than f of x plus delta x. So now let's actually take a moment and think what happens when delta x tends to 0. When delta x becomes 0, or not becomes 0, approaches to 0. Actually, let me introduce the limit symbol. It might be more complicated, but let me still do it. So let's say if delta x goes to 0 for f of x, and this is less than equals to limit delta x approaches to 0, delta a over delta x is less than equals to limit delta x goes to 0, f of x plus delta x. Okay, so what happens to this function f of x? You know, since there is no delta x, it will be simply f of x here. F of x, sorry. That is equals to or less than. What is this function, by the way? So delta a or delta x, where delta x goes to 0. You see, delta x actually is the change in the y value or change in x value, which is like a slope. But then this is the slope when delta x approaches to 0. So this gives you, by definition, this is the derivative function. Okay, we have discussed this thing before. So this is actually dA over dx, and that is less than or equals to. What happens to this function when delta x goes to 0? So this function becomes equals to f of x. Okay, if that is the case, dA over dx, which is the derivative of a, is more than or equals to f of x and less than or equals to f of x again. That means dA over dx equals to f of x. Okay, and this is actually very, very remarkable thing. Let me change the color to green. Let me rewrite this equation. You know, dA over dx equals f of x. But what is a, by the way? Do you remember what is a? We have defined a beforehand earlier, right? A was this. The area, if we have the whole area, if we combine all the area, a was this, right? So let me replace a with this function and see what happens. So we have d over dx, and then instead of a, let me write this function f of, I don't know even what is this function right now. Okay, and this is equals to f of x. And now actually what we see here, what is happening, this was some function, I don't know what is this, I call it s function. But then, you know, once you have f of x with this function, the derivative and this function, somehow they cancel each other. Why? Because on the right hand side, I get f of x. So this is actually very remarkable concept, that the derivative function and this function, they are opposite. In other words, integration, and let's call it integration. Integration is the opposite of derivative. And that is actually the fundamental theorem of calculus. And this is actually not a very, very obvious thing. The area under the curve happens to be the opposite function of the derivative. And, you know, the derivative we have defined that it is the slope of the function, and the integration was the area under the curve. And apparently there is no connection. But with this fundamental theorem of calculus, we realize that the derivative is just, or the integration or the antiderivative is the same thing as the integration. So that means in order to find the area under the curve, I don't need to basically add all those strips. I can simply find the antiderivative. And we know how to find the antiderivative. And that would give me the area under the curve. Make sense? Thank you, Naresh. I think this you asked this question, I think, in the beginning. So this is actually very much revealing concept of integration. And based on this idea that, to find the area under the curve, which is the same as finding the antiderivative or the reverse differentiation, which we all know how to find it, we can simply give the answer of that seemingly impossible question of how to find the area under the curve. Because to find the area, you can only find the area of regular shapes, rectangles or a circle, and so on. Thank you, Naresh. By the way, for example, we only know as a human or as a standard way, we only know how to find the area of a rectangle and nothing else. Like from the area of a rectangle, which is length time width, we have to find, like the area of a circle, pi r squared. You might have wondered why the area of a circle is pi r squared. Actually, it is calculus that gives you the answer of this. Maybe if time permits, we can discuss this thing. But any other area formula comes from calculus mainly. The only formula which we can simply just take it as for granted is the area of a rectangle. And anything else, it has to be from. We have to find a formula using the calculus, the idea of integration, and so on. So the volume of a sphere and the volume of a cylinder and the surface area and the area of a circle and so on has something to do with the calculus. All right, so this is actually the very idea of integration, and then again there is a formula and the formulas, different rules and regulations for the integration. And let me actually not discuss those things with you. So basically, the area under the curve is the integration, and remember, it is not obvious that the area under the curve is the opposite of the differentiation. It takes fundamental theorem of calculus to ensure that the area under the curve is just the antiderivative. All right, so let me see what we should do now. Yeah, so this is definite integral and the area under the curve. Okay, let me skip all these steps. Let's move on to find a volume of an object using the GeoGebra and using modeling. Okay, because I think that is going to be very much revealing. So I want you to be with me. What does modeling mean, by the way? When we say mathematical modeling, what are we doing exactly? I mean, you don't have to tell me the mechanical definition, just in a very layman term. What is modeling? When we say modeling or mathematical modeling, what do we do? And why do we do so? Sorry. Yes, anyone? So while you write your answer, let me find out. Let me try to change the screen. Start. Give me a second. Yeah. So mathematical modeling, coding. Okay, Imran Abbas is saying coding, finding differential equations to connect variables. Okay, this we code actually, or even we find our differential equations and so on. Actually, like we use it to make a mathematical model. Actually, when we say a modeling, is because what we do actually there, we find a physical phenomena and we want to find out a mathematical formula out of it. Okay, it's because once you have a mathematical formula, then math gives you so much power. Then you can of course predict even the future, because you can see how the formula is behaving, and especially if you use calculus, you can see how it is going to be changed. So for example, if you happen to be a super mathematician and if you see a trend in the stock market, and if you come up with a mathematical formula of how the value of the share in the share market they are changing, and if you come up with a mathematical formula, or of course that will involve a derivative or the calculus because they are changing. So then you can also find out when it will give you the maximum profit, and then you can invest accordingly. Okay. So likewise, if you also making, let's say, a car, you want to maximize the mileage, and you want to minimize maybe the air friction on the wind. So one way actually is to make a different types of car and then do it in practical way. Another way is to make a mathematical model and then use the very idea of derivative, maximum, minimum, and optimization to find these values. That also means if you learn math, it is also going to save you a lot of money. Okay, so it's not actually just for fun, but you can also save a lots of money if you really learn the calculus. Okay, so where is that? Just give me a second. Let me try to find out. Yeah, no, it's not this one. So now actually we are going to see, we will be doing a mathematical modeling on GeoGebra. It's a very free, as you know, it's a very totally free tool. There's no money attached at all. So we're going to do a mathematical modeling there. I want you to just understand a couple of things from here because we will be using them. So it's better if you see this. To find x coordinate of a point, so we use the small x of p. So if you do so, it will give me the x coordinate. So in this case, it will give me the value of a. And to represent the y-axis and x-axis, I will type x-axis and y-axis. And be careful, the GeoGebra is case sensitive, so you also have to write this way: x small and then a is big. The last two, to create a surface, there's a formula. Surface, and then you have to insert the curve which you want to find the surface of a curve. So you have to type here the curve and then the angle and the line of the symmetry. And to rotate a function, you have to write this code, but you don't have to memorize, because once you simply write rotate in the GeoGebra, it will give you all these options. But right now, I just want you to understand what is happening here. So if you want to rotate anything, you see it says object. So we can rotate a function. We can even rotate any object. So that's why they are calling it object. And you also have an angle. So how much angle you want to rotate the function, and also the axis of rotation. So we will also see this thing. The last thing is very important. I really want you to internalize this idea. Curve fitting. So we will also be using the curve fitting, and for that actually there's a function. It's called fit poly, and poly here means the polynomial. So we are actually trying to fit the function through some polynomials, and inside the function we are going to put write down the points which we want to make a fit using the polynomial. And here we have to find out the degree of polynomial. So is it going to be a first order, second order, third order? So this is actually the last part is like a trial and error. You will find first with the maybe second order polynomials, the third order, fourth order, fifth, sixth, and you'll see which one works best. So let's see this. Let's see them in action in our GeoGebra app. Okay. How much time do we have now? I think we do have 15 minutes, right? I think it was 2 hours and 15 minutes. So we have 15 minutes, and I think we should be able to do it in 15 minutes time or less. Okay, so let's get going to our GeoGebra. Right here, GeoGebra. Oh, actually, there's also an app. Let me use an app, GeoGebra Classic Suite. Okay, I think I need to share my screen again. Second. Yeah. Just give me a second. I need to share the screen. Here we have it. So you can also install GeoGebra on your computer if you're using Mac or Windows or even mobile phones. They have an application for all the platforms: iOS, Android, Windows, Linux. Okay, Ghulam Farid, you have a question, so go ahead. Okay, let me clear this thing. We will be doing this kind of animation in a while. We will be working together. So you will see like this. Yeah. Okay, let me just actually clean this. Sorry. Okay. All right, let me clear this screen. Is that? Okay, I guess I can select the first part and then the last part. If you shift click, then you can delete them all. And or let me actually quit. So let me reopen GeoGebra. Okay, by the way, if you have any question, you can also ask on the chat box, or you can even raise your hand if you want to speak to. No problem. Let me see, how can I share the screen now? I don't see it. Yeah, it's here. Okay. Do we have any questions so far? Okay, so we have art of translating problem from an application area into tractable mathematical formulation. Why we are making it difficult for simple person? Okay. Yeah, actually, you know, it's not actually we are making it difficult. Yeah, you might feel that you are making it difficult. Actually, I think if I understand correctly, we have a question that why we have to make a mathematical model out of it, because apparently it seems difficult, right? Yeah, it might seem difficult, but it's not actually the criteria is not the difficult or easy. The criteria is to be more meaningful or beneficial. So which one, like if you have a mathematical model, it is more meaningful. Okay. So in life, we are pursuing not we don't actually pursue the easy or the easy task. We are actually after meaningfulness. So that is our essential idea. So for example, you know, the multiplication, let's say 2 times 2 times 2 times 2, right? Or, you know, if you add 2 4 times, 2 plus 4 plus 4, sorry. If you add 2 4 times, 2 plus 2 plus 2 plus 2, you get 8. But then we also invented 2 times 4 is also 8. So the multiplication might be more difficult than addition, but it also helps you a lot. Okay. Similarly, integration might be more difficult, but it is also going to help you. Okay. So it's not actually about having an easy task or things. We are actually after meaningfulness. So that is the criteria. And by the way, I will also recommend in your life when you do math or it can be anything. When you are doing anything, you should not be actually after the comfort or easy things. You should be after meaningfulness. That is actually how the life gives you. You become more productive. Okay, I think now you can see the screen. I hope I'm able to answer you, Ghulam Farid. So let's continue. We are doing the mathematical model, and actually we are going to find out the volume of some particular things. Meanwhile, if you have more questions, feel free to type in the chat box. I will see if I able to answer you while we do this modeling together. So just be with me, and if you have any question, you can also interrupt me and ask me. So this is actually like interface of the GeoGebra, and this one actually is graphing portion, and here this is the input. You can also write down the functions here. And actually, let me find out something. Okay, let me remove this grids. Yeah, it looks a bit irritating. And let me I want to make a mathematical model of a vase, for example. So let me click here, and then it says image. I can also upload image from here. So let me choose a file, and let's pick this beautiful looking vase. And here we have it. It seems a bit bigger. Let me even make it small like this. And I can move around. Of course, you know, I'm using a vase. You can also use any other thing. For example, if you want to find out, let's say if you're making a new product, let's say drinking water, and you want to make a bottle of drinking water, like a new design. So you want to maximize the volume and you want to minimize the surface area, because, you know, the surface area costs you plastic. So if you want to minimize the surface area and maximize the volume, so you will be also doing the mathematical modeling and so on. Okay, so let me insert this picture, and if I right click on it, I can click on the setting, and let's make it a background image. So it can go at the background, and then I can see my axis. Okay, Let me close it and let me even enlarge it. This. Okay, to make a mathematical model, I need to make a functions which is going to be a polynomial function. And as we discussed, a polynomial function, we use it because polynomials are very well behaved function, and they are very nice and kind function. So generally, when we do a mathematical modeling, we use polynomials. Okay, so just be with me. So I need a couple of points. So let me click on this portion here. It says add point. So let me click here points, and let me click some on the curvature of this. You should not be putting them too close and also too far, then it might be a problem. So let's put some points here and on the surface, and like this, and like this, and like this, and maybe like this. Yeah. So we have got points from C, D, E, F, G, H, I, J, K, L, and then I want to find a function. Now actually this is very important. I want to find a function which is going to be a polynomial that passes through all these points. Okay. So for example, I will write here fit polynomial fit. Yeah, fit. So you see, let me select the first one, list of points and degree of polynomial. So the degree of polynomial actually means the polynomial is going to be a linear function, a quadratic function, a cubic function. So right now we have no idea, because we want to see. This is, as I told you, it is going to be trial and error. So let's before I use this fit polynomial function, let me define a variable. So if you simply write here n, if you press enter, then actually the GeoGebra gives you, gives you a slider, and you see this n changes its value from -5 to +5. But since we know the degree of polynomial has to be a positive number, so let's make it 0. Sorry, let's make it 1. And the maximum value, let's make it 10. Because more than 10 would be much more tricky. And the step, it should go with 1 step, yeah. So now actually, if you move this slider, the value of n goes from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like this. Okay, now let me use the function polynomial fit. So fit. By the way, there are different types of fit. As you can see here, fit exponential, fit growth, fit implicit, fit line, and so on. But as I told you, fit poly is the most used function. Okay. So which one is? So fit poly, and the list of points and degree of polynomial. And list of points, by the way, is all the points, C, D, E, F, G, H, and until K. So in order to write the list of points, I will be using the curly bracket. So C and D and E and F and G and H and I and J. Sorry. J and K. Okay, let me even enlarge this. And so this are the list of point. Let me delete this. And the degree of polynomial, we have to find what is going to be the best degree of polynomial. So let me write here n. And as you can see here, n is a variable, and the value of n goes from 1 to 10. So we will see which value of 10 would give us the best approximation or best model. So let me press enter, and let me actually make it small like this. And as you can see here, when n is 1, you see we have a linear function, and of course it does not fit. It does not go through all the points. You see, so that is not actually going to be a best model. I want a function that would give me, that would give me that would pass through all the points. Okay, let me change the value of n. If n goes from 1 to 2, this becomes a parabola. As you can see here, it's better approximation, but still not good. Okay, let me change it to 3, much better. 4, okay, good enough. Let's see 5. You see 5 is even better, and 6 we have, and 7. So you can choose between 7 and maybe 5. Okay, let's choose 7 maybe. Yeah. Actually, even if you go further, let's say 10, 8, 9, 10, but it's not recommended to go like a higher order polynomial, because then they become very much, they fluctuate a lot. And also the calculator, your computer must be very much strong to deal with all those higher order polynomials. So it's good to have as small degree of polynomial as possible, but that depends actually. And also, I still have some error here. You see this error, and this error is because of my points, they're not good enough. So this actually, the fitting things, it might take a while. You have to try, you have to put the points at different places. There are also some tricks, but I think this is good enough. The error is not, I think is not that much. So we have this function basically, this polynomial, and as you can see here, the polynomial is, these are the values. So this is the polynomial we want to work with. Let me define a new function, because I don't want the full function. This polynomial, it goes to negative infinity to plus infinity. I want function starting from C to K. So let me define a new function. As you can see here, function, and then start x value and end x value. So let me select this one. So I want the new function to be defined from the f of x, or f, which is the same thing as f of x. The starting value is going to be the x value of the point C, okay, and the end value is going to be the x value of the point K. Yeah. So you see we have this new function which is also labeled in red color, starting from C to K. Let me turn this green function off. So now we have this function, you see, this curve. So this is actually like a mathematical model of the curvature of the vase. And now I want to rotate this guy. So if you simply write here rotate, so I get this options. Rotate object angle, we have rotate object angle, and let's select this, the third one. We have an object which is this red function, this polynomial function, and we want to rotate this function with to 360 degree or 2 pi degree, and axis of rotation is x-axis. But again, I want, when I rotate with some angle, I also want to keep changing the angle. So before actually I use this function, let me define another parameter. Let's call it k. Another variable, so let's call it k, and k goes from 0 to 2 pi. So it's good to use the radian, by the way, in mathematical modeling, 2 pi, because radians are more natural units. And the step is, let's call it 0.01. Okay, what is this? Okay, by the way, I think it's already the time, 3:15. Okay, if you allow me maybe 2 or 3 more minutes, let me finish this very soon. I'm sorry that I'm taking your time. Let me quickly find the rotation code, and here we have it. The object we have is g. This is the function g, and the angle this time is going to be k, and axis of rotation is going to be the x-axis. Okay, x-axis. Okay, let me change the value of k. Yeah. So as you can see, this function g1, it is a rotation function, and if I move this, like the value of k from 0 to 6.28, you see that this curve is rotating, right? But you don't see, or do you see it? Yeah, the curve apparently is not moving, and it is because this surface, this interface is 2-dimensional interface, and I cannot see the 3D thing in 2D, right? So what I will do, as I told you, GeoGebra is very, very powerful. If you click on this guy, actually on this guy, and if you go to view mode, you can also select 3D graphics right away. So it will add 3D graphics into this same interface, and I can see this curve on this interface. Actually, let me make it small, like this. Okay, yeah, let's like this. So you see, if I now move the value of k from 0, actually let me even play it. So you see these things, they are, it is moving now, okay? So you can see that this is how the curve is being rotated. Actually, let me make it even more visible. Show Yeah. But this is actually like the curve is rotating in 3D. You can see it from here, and you can even make it more. It can be more visual, and it can make it home. Yeah. Okay, let me also define a new function which is called the surface. I also want to see the surface of this thing, because if you are talking about the volume, it is going to be the, I need to see the surface. So surface, curve, angle, and line. So sorry, delete this. And let me pause this guy. So surface, if you write here surface, and then we have this option, curve. So the curve is G. And angle is K, we have defined up earlier, and the line is X axis. Yeah. And now actually, if we need this curve, the angle, we see that we have a volume of this guy. So this is like a mathematical model. So you can make a model of this vase. This is actually, you might see that why we are actually making a volume or the model of vase. I mean, again, it's a starting point. But if you're doing any engineering projects, you can think of any, for example, a car or any physical phenomena, for example, the temperature in the room, how it changes from one corner to another corner, how probability distribution is changing, like so many things you can come up with. If once you understand the basic idea and you see this nice curve, you can make it, you can even download these things, these pictures. If you click on it, you can simply, yeah, of course you can do so many other things. Since the time is not favoring us, I can also recommend you, if you simply go to the GeoGebra tutorial or help page, if you simply type there GeoGebra command, you can simply find out many different options. Let's say implicit functions and implicit derivative, and so on. Okay, so let me stop here. After this, of more mathematical modeling, you can also do many interesting things on this. And let me just go back to our slides. And there's that. Actually, it's the time already. And again, let me apologize for taking too much of your time. There's that. Yes. So yeah, right now we end up here, and I want to thank you all. So if you have any question, let me know, or maybe Miss Mohsina, if you want to say anything. If you have any comments, any feedback you want to share now, you can do so. And yeah, and that's it actually from my side. So please, if you have anything to say, please let me know.
Namira, I'd just like to add a few things. Namira has said that how to get CERN certification. I think that's a direct question to Hasan. Before you answer, I'd just like to say to everyone that you can let us know your feedback. You can email Hasan, you can email me. I believe all of you have Hasan's email address, and you can also stay in touch with him. I think what he has done right now is just introduced you to these new tools. Now it's up to you how much you want to learn them further. So as you go along, you can, I think, definitely reach out to him for more guidance or to discuss anything new that you come up with and similar.
Okay, yeah, thank you so much. Actually, I want to say here, let's say next 5 minutes or let's say until 7:30. If you have any technical question related to this topic, you can ask. And after that, I can still maybe spend maybe 5-10 more minutes. If you need any other question, let's say about CERN and CERN certification, those things, I can also respond to you. But let's maybe for next 5-10 minutes, if you have any question related to calculus or GeoGebra, you can do so now. Otherwise, I can also answer you the questions about CERN certifications and so on. Let me see what do we have here. How to contact if you have any question. I shared my email with you, and you already have the email of, I think, Mohsina. Very interesting. Maybe not for college level students. Oh, no. It is actually for college level students. Yeah, unfortunately, maybe FSC syllabus is not very good enough. But actually, if you're doing IB, which is also a college level certification, it is immensely helpful. And also A levels. Okay, then we have modeling was the best part of the session, although in the start we learned many things. Okay, thank you. And knowledge, okay, thank you so much. I want same thing in Python. Yeah, actually you can do same thing in Python, of course, even much better than GeoGebra, but GeoGebra is more intuitive. So if you want, so please explore. There is also many interesting options. If you really want to learn Python, for example, codecademy.org, I really recommend you to work on that. And GeoGebra and Desmos is best for college students, exactly. Okay, any other question? Kindly arrange another session on Python. Okay, we have done a course on Python earlier. It's, yeah, okay. So Mohsina has answered. There's already a course on Python. And if you need more course, you can of course contact her. So maybe she may be able to arrange with another instructor. I'm not actually very much proficient in Python. I have some know-how, but not very well. Cool. Okay. Okay, I think that's it. It seems if there's no more question, then I can maybe discuss some other question also. By the way, I also want you to let us know if you need any other session, maybe on another topic. It can also be statistics, for example, or any other mathematical topics, or even physics, can wish. Okay, I think that's it. So how to get CERN certification? So if you're a teacher, the CERN also provides you a summer teaching certification program. It's like a 3 weeks program, which is totally funded by CERN, but it's very, very competitive. There is an application process. I think it starts in December or November or December. I can share the link if you send me an email. So, but you have to be a teacher, especially high school teacher. You have to apply, and the process is very competitive. Pakistan is also eligible, but actually I joined CERN when I was in Denmark. Then it was much easier, but even people from Pakistan, they have participated. The CERN has trained them, so you can do so. Yeah, so you can apply, and there is a procedure and so on.